Well, good evening, everyone. Welcome to the RINA event, the Royal Institution of Naval Architects, kindly hosted by Engineers Australia. My name is Piotr Zukowski, and I'm the chairman of RINA WA section. To acknowledge the land that we are on, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders both past and present. All right, so without any further ado, I'd like to introduce our first speaker and the first topic of tonight's presentation, Dr. Wenhua Zhao, who is the Senior Research Fellow at the University of Western Australia. He will present a topic on innovative experiments for wave interactions with floating structures. So a few words about Dr. Wenhua Zhao. He is a DECRA fellow.
Yeah.
You can tell us what DECRA means. This is a special acknowledgement, I think.
Yeah, that's a ERC-funded position, which is Discovery Early Career Research Award.
Yep.
That's a fellowship, yeah.
It is indeed. He's also a Shell-funded Senior Research Fellow at the University of Western Australia. His research focuses on hydrodynamics and wave structure interactions, which has led to more than 70 publications spanning from the most renowned academic journal in fluid mechanics to most industry-focused conferences. Wenhua has been serving as a chief investigator for the Offshore Hub and the Tide. He was elected as a Bi-Fellow in 2020 at Churchill College of Cambridge University, and he is currently a deputy editor for the Ocean Engineering Journal. Well, I'd like you to join me in welcoming Dr. Wenhua Zhao for his presentation.
Yeah, thanks for the introduction, and good evening, everyone. And today I'd like to use a couple of slides to talk about the studies funded by the Research Hub at UWA. And I'm going to talk through three topics in general, subtopics. One is wave-induced ship motion. The other is gap resonance, relevant to side-by-side offloading ship-to-ship transfer. And then the third one is groundwater event, which is associated with extreme sea-state response. And so to start with, I'd like to use a video to show you what is like a ship motion look like. And this is a cruise and experiencing some roll motions. And if you are sitting in a cruise, what may occur? So this is what may occur when you experience like a roll motion. And this is a video taken inside of a carrier, a cruise carrier. Yeah. Yeah, so that is a ship motion, and I call it like cruise and crew coupling. And from engineering practice, we are interested in for LNG carrier, we're gonna be interested in the ship motion coupled to the liquid cargo inside of the tank, and that's very complex hydrodynamic phenomenon, as you can see. This is the movie shows the tank sloshing inside a spherical tank, and the ship motion is driven by a regular wave. Now you can see that's a regular wave driven ship motion, and the sloshing is quite not regular anymore, as you can see, the swirling and other sloshing mode inside. And this is a tank testing we conducted in Shanghai Jiao Tong University, and the wave basin is 50 meters long and 40 meters wide, and the water depth was 10 meters. So that's very deep water wave basin. And through this study, what we found, we identified the, as you can see in the picture on the left-hand side, that is a spectrum of the responses, which covers the raw motion and also the sloshing inside of the tank. And quite complex picture that is, all the, each peaks corresponding to like a sloshing mode inside of the tank. So we identified the different sloshing modes inside of the tank and also identified the coupling mechanism between the sloshing and also the vessel motions. So it enables us to better predict the ship motions with more confidence or more accuracy. So this is something we did for raw motion coupled to liquid cargo sloshing. And we are also interested in another scenario, which is if we have a vessel parked at the ocean against another vessel, for example, the ship-to-ship transfer or side-by-side offloading. And we want to know what is the raw motion will look like and what is the role of the viscous damping compared to a single vessel when you have another vessel nearby. And so this is some work done by my colleague Ian, who is sitting here. And this is a quite nice piece of work in 2D. And what we did here is we run the CFD simulations, and also we run the PRV testing. And as you can see here, this is the like a transparent rectangular box, if you like, and this is a vertical wall. So that is a section of a ship section rolling against a vertical wall. And we use very sharp corner here because that's a representative of the bilge keel, for a vessel. And what we found here is, the vertex shading from the sharp corner can be the dominant source for the hydrodynamic damping for the raw motion of this model, and also for the gap resonance inside, between the model and the vertical wall. And here because of the presence of the vertical wall or the second vessel, and the fluid field can be modified, and then the vertex dynamics can be modified, and therefore the overall damping will be changed compared to a single vessel. And so we summarize these observations in a paper written by Ian, and that's a collaboration work with experts, hydrodynamic experts from France and also from UK. And we did some testing in France, and also collaborating with developing the numerical code with the Bernard Mollin and expert from the UK. And then move forward to the second topic, which is the gap resonance phenomenon, which this again is a video and show you what is a gap resonance look like. So this video is a ship-to-ship transfer, and the far field is the ocean, and you might notice that the wave condition is very mild. The background sea state is very mild, but what you may expect inside of the gap is like this. So outside is very mild sea state, but inside of the gap, you can see here, we have very strong resonant motions of the water inside of the gap. So this is a gap resonance phenomenon, and that's a very interesting hydrodynamic phenomenon, as you can see here. So this is relevant to ship-to-ship transfer and side-by-side offloading and some other, multi-body interactions. And to look at this problem, because you can see that's very strong resonant motion and the nonlinearity and viscosity all coupled together. It's really hard to predict that. And then we did some testing in the same wave basin in Shanghai again. And now we focus on the physical understanding of the gap resonance problem. So we kind of simplify the geometry. So we use two rectangular boxes, and we combine these two boxes together, which are like two fixed ones. And we are focusing on the gap resonance inside of the gap. And on the left-hand side, that is like a snapshot of the experiment. And you can see the yellow color is the model of the sitting in the basin, and connected with the blue, like the gantry, which is a very strong gantry. And the model is like 3.3 meters long, but too small compared to the wave basin. The benefit of that is we don't, when we do the testing in the large wave basin, it allows us a large measurement window before we get any contamination of the surface elevations from the side of the wave basin. So here, this is a slightly higher level of the demonstration of the experiment. So the yellow color is the two boxes again, and then we have we generate a transient wave group. The time history shown on the top left corner, and then we send this wave group pass through the two fixed boxes in the basin, and then we measure the surface elevation inside of the gap. And then the red color is what we measured inside of the gap. So the interesting thing here is, this is a linear excitation, and because we designed that in a linear way. And if you look at the input and the output, it's already very complicated and not intuitive now. So it's really, by not intuitive means if you look at the input, it's hard to predict the output. And the output have a very strong beating pattern, which is relevant to the like a gap resonance mode. And that's a superposition of the various gap resonance modes inside of the gap. And to show you what is the gap mode look like, is this grain curve. That's a half sine signal, or half sine wave, if you like, from one end to the other. And that is the first gap mode, which means, like that way. And then we also have other gap modes, which is three half sine wave along the gap. We demonstrate as the red color, the red curve. And now I'm going to show you with animation about the gap modes. So imagine that if you hold a string, the two ends of the string, and oscillate up and down at different frequency, what you're going to have. So this is what you might have. So if you oscillate at different frequency, you can excite the different vibration mode of the string. And similar idea, if we have a wave group contain all the frequency of interest sent into the gap, you can excite the different gap resonance mode. And that is similar stuff between mechanical vibration and watt resonance. Here, so what we're going to do with the measured data So in the engineering design, we wanted to obtain the RAOs. RAO is a linear transfer function. Before we do that, we're gonna look at the data. So now we have the time history for the input and the output. If you do a spectrum analysis, and then you can have the information about the energy distribution for the input wave energy and the output response. So here on the top right corner, that is the power spectrum of the input and the output. Again, the blue color is the input wave energy, and then the red curve is the response corresponding to the curve on the bottom corner. So if you use the red curve divided by the blue curve, which is the output divided by the input, give you the ratio of the output against the input, which we call it RAO, and that's essentially a linear transfer function of output to the input. And that's very important parameter when you design the offshore structure. And here the dots represents the results we obtained from the previous slide. And you can see the quite a few different peaks, and maybe not so obvious yet, but I'm going to show you my numerical simulation, because we always want to know if we can numerically predict the experimental results. So this is the prediction based on linear potential flow theory. Now you can see we have very good agreement in the peaks. I mean the frequency for the peaks, but the amplitude from the numerical simulation has been overestimated, a few times bigger compared to the experiments. So what happened there? The reason is that this is like a demonstration of the setup, and because in the numerical simulation for the two vessels, and we only consider the blue color and ignore the red color. The red one is the viscosity. So that means we ignore the viscosity contribution. That's why we overestimate the prediction or the responses. So it's important to understand the viscosity here now. To understand what is the nature of the viscosity here, we had a PhD student Hong Chao Wang who did CFD modeling for the two rectangular boxes, and this is animation of his CFD modeling, and that's a huge effort actually, because this is if you look at the model, that's 50 million cells, and we solved the wave field and also the boundary layer field. That's quite a different scale. One is a huge area, the other is so tiny, but you need to solve the two scale problem at this one go in one model. So that's something quite novel. And also it's very time consuming. And because as you can see in the previous slide, that's only like a 30 seconds time signal, right? And we use this CFD model to reproduce that 30 second time signal. And we use the superpower, the superpower computer in WA, and it took us 30 days to run 30 seconds simulation, which is, this video took us 30 a whole month. And but that's quite a nice output, because it gave us the very detailed visualization of the fluid field, and gave us the confidence that the viscous damping here is actually a Stokes type lambda boundary layer, and that's for this type of viscosity that it has a linear property. If that part is linear, all the previous part is linear, so that's very good observation and very useful observation for industry, because then you can save time. Everything can be linearized. And then we use that model to use the linear viscous damping to collaborate with our industry partners. And we collaborate with DNV, Bureau Veritas, and the Lloyd's Register, and each of them have their own commercial softwares. And we use our observation, the viscous damping coefficient, as the input for them, and then they produce the solid curves, each color representing the different company as software. And what we can see here, the solid curves match quite well with the experiments now. So that means all the current commercial software have the capability to capture the strong resonance phenomenon by incorporating the viscous damping coefficient in a proper way. And we developed some recommendations on how to determine the viscous damping, even if you have different software or different methodology to consider the viscous damping. And we have a uniform equation for all of us. So that means that saves engineers a lot of time, because you don't need to worry about if you change from this software to the other one. You need to change the coefficient and justify why you need this coefficient and how you select that. But now, we unify that. And this one was incorporated to the new design guidelines developed by Lloyd's Register at the end of 2019, and also contributing to a large grant we secured last year, which is the ARC funded research hub. We call it TIDE. And again, we are collaborating with quite a few partners, including Woodside, Shell, Impex. And so that is the second one. And I will quickly go through the third one, which is extreme conditions, which is groundwater event. And this work is done by my colleague Li Fenchen, who is, I guess, online now, but she's stuck in China. So, but for the audience, maybe better for me to go through the slides. And so for this project that's relevant to the safety of FPSOs, and so what is groundwater? And it's actually probably that's because the color is green. You call it groundwater, but more academically, the definition is that's essentially a large volume of water overtopping a deck on the FPSO. That is groundwater. And then the purpose of this project is to improve the prediction of the risk of groundwater occurrence, and that's relevant to FPSOs, both disconnectable or connectable. And here, this slide shows some pictures of the groundwater event. And this is very like the current engineering practice. When we think about groundwater, we usually divide the groundwater event into 4 steps. One is the on the very top, and we call it the freeboard exit stage, which is the water moving up. And then the second stage is actually the second, third, and the fourth one are all pretty much the water shaping on the deck. And the second one is the beginning of that, and the third one is moving towards further, and the fourth one is you got a topside module on the deck and hit the module and may cause some damage because of the groundwater event. That's why we are interested in the groundwater event. And so the problem for this is we divide that in which is into 4 stage, which actually a bit arbitrary. Yeah, no physical meaning for that, and that's just facilitate our analysis. So then, to better understand the whole process, we also did a series of testing in the wave basin in Shanghai, and try to figure out what is the most relevant, or what is like the role of the linear excitation as the nonlinearities. And here, this is a model for that. And the model is 5 meters long in the basin. And it's floating in 6 degrees of freedom. And what we measure here is we measure the surface elevation at the hull of the vessel, and also we measure the impact force because of the groundwater, which is on the top but not shown here. But on the bottom picture, you can see that this is a groundwater event hit like this area, which is this is a model of a topside structure, and then we have groundwater to hit to the structure, and we measure the impact force. And so this is a result. We not only the experiments but also CFD modeling, and on the left hand side, that is decomposition of the different components for the from the CFD simulations, and on the top, that is the linear component, which is the frequency lined up with the incident wave frequency, and then the bottom one is the second harmonic. As you can see here, the second harmonic is much shorter wave compared to the linear one, because the second harmonic is essentially the frequency is double of the linear component, and then the wave frequency, the wavelength will be much smaller. And also on the right hand side, that is the time histories we measured in front of the bow, which is demonstrate use the red dot, and here. The first one is the total signal we measured, and the following one are the decomposition of the different harmonics. And the third subplot, that is eta 1, which means the linear contribution. And then we have eta 2 plus, means the second order some frequency contribution. And the eta, which is the top second one, eta 2 minus, that is the second order difference term. So each contribution are listed here and quantified. And what we found from here is by the response amplitude, only the linear and the second harmonic are important, and the third harmonic is variable but much less important, and the higher order can be ignored. So essentially, if you want to develop a more efficient model, you can look at the linear contribution, and also consider the second harmonic, which includes difference term and also the sum term. So that is the groundwater event. And to ramp up, and today I have covered the raw motion, which is a single vessel response to incident waves, and coupled to internal sloshing, and also consider a vessel rolling against a second vessel. And then they also talked about the gap resonance, which covers the RIO's calculations, and identifies the nature of the viscous damping, and also the research has led to guidance to help industry to in the numerical simulation of the side-by-side offloading or ship-to-ship transfer. And the third one is the groundwater event, which we identified the relative contribution between the different components. By components, I mean the linear contribution or the higher order harmonics, and up to which nonlinearity we can stop, because you don't, it's hard to go to infinity. So, and also actually what I didn't show is, because that slide was too complicated, I think. We also identified what kind of waves will give you the largest response. Because we are interested in the extreme response, but also from the physical side, we also wanted to understand what kind of waves will produce the largest response. And from that study, we also identified that